Hi, good afternoon. We are trying to we are going to prove following theorem. Any continuous function, right, matrix X, another matrix space Y need not become. I want to show it to us. So it is uniformly. Yeah, theorem. Somebody has requested me. I just saw the request about few minutes ago. So I decided to give the proof. Okay. First, let us recall. Suppose I have two matrix spaces X from X to Y. And I say this is uniformly continuous on X. Okay, all metrics and Y are metrics. Uniformly continuous X. If is also important. And don't say simply uniformly continuous. Uniformly continuous on which set you should say X. If for any given epsilon positive, there is a delta positive, so that for every pair x1 x2, okay, in X with the condition distance between x1 x2 delta should have distance between fx1 and 2 and epsilon. Okay, this is uniformly continuous. Most often, the textbooks or teachers may say uniform continuity is continuity where the delta is independent of x. That's not the way to say that. Okay, that's a corollary of the definition. Okay, just before going further, let's try to understand this definition. What does it say? I have x here, I have another y. Okay, so what does it say? Suppose you give me an epsilon positive my f, no matter where I take points x2, okay, or x1 x2 here, or x1 x2 may be here, or x1 x2 may be here, or x1 x2 may be here. I don't care. Okay, I don't care where the two points are there, but as long as their distance is less than delta, then I know their images I have to look at. The images may be anything, I don't, right? So this may be fx1 fx2, and this may be corresponding f corresponding these 2 points, and this may be corresponding to these 2 points, and this may be this point. But what I want is these distances will be less than epsilon, provided I know these two distances less than delta, then this is less than epsilon. Okay, so to talk about uniform continuity, I have to start with the pair of points. Okay, now just to make sure, as a corollary, this definition says, so the first observation is, what is the observation? If f is uniformly continuous on X, then to prove f is continuous, what should I do? Fix a point A, take any arbitrary point, then I have to show is continuous at A. Yeah, to show this is continuous at A, you will give me an epsilon positive, then I have to choose a delta. What delta I will choose? Since epsilon is given and f is uniformly continuous, okay, by definition there is a delta, a uniform continuity, right, corresponding to the epsilon. Therefore, if I take any point in BA delta x here, then distance between x and a will be less than delta, and hence distance between x will be less than epsilon. Understand that? So, as a corollary, whatever point you take for the same epsilon, I will choose a single delta. I will get a single. Okay, this is a corollary of the definition. But you should remember, whenever I want to show something is uniformly continuous, I should not get fixed at a point. I can take any two arbitrary points, okay, in the domain, so that their distance is less than delta. Okay, so you are not fixing a point and working within the delta open ball around the point A. That's not correct. Okay, now let's go to the proof of the theorem. That proof is actually easy, but unfortunately people make a guess. Let us look at, okay, proof. Let us first see what is the idea of the proof. Okay, idea, and then see why I should change or modify or improve upon this idea. Okay, so let epsilon be given. I want to show f is uniformly continuous. Let epsilon be given. Okay, then for it is uniform, since uniformly continuous function is continuous at each and every point by observation. I'm sorry, I want to show f is uniformly continuous. We know f is continuous, therefore for any given x, okay, f is continuous at x. Therefore, for this epsilon, there exists a delta x. Yeah, maybe let us call it R. So Rx positive, so that for every y in Px Rx, what do I have? F of y belong to the open ball P of x epsilon. Understand? Notice that unlike again textbooks, I don't let dx denote the metric on x and dy denote the metrics on y. I don't write that. The context should make it clear, because where is fx is in y, therefore this is an open ball with respect to the metric on y, and where is x in x, therefore this is an open ball in x with respect to the metric on x. Okay, I don't want to write that such thing, okay, because I believe my students and viewers of this video are all intelligent. Okay, right, let's come back. Okay, therefore you can see I have an open cover of this, like this, as x varies over capital X is an open cover of x. Since x is compact, I can choose a finite subcover. Let us say there is x to xn, so that pxj rxj, which we will call it as rj, bxj rj. This collection, as j varies between 1 and n, is a finite subcover. Okay, now you would expect if I take delta to be the minimum of Rj, is our expectation, will work. This is what we wanted, but unfortunately this may not be true, because if I take x and y, so that distance between x and y is less than delta, okay, how will I argue? I know there exists a j, let us say there is an I, so that x belong to p xi ri, yeah, and similarly y p xj rj. Okay, and I know because of this d of fx and fxi, that will be less than epsilon, and similarly distance between fy and f of xj will be less than epsilon, but that will not tell me how to connect between distance between fx and fy. You understand that? Because when I want distance between fx, fy, I will try to split it like this: distance between fx and fxi plus distance between fxi, fxj, and plus distance between fxj and f of y. So this will be less than epsilon, this will be less than epsilon, but I have no idea about this. X1, xi and xj are 2 points. I have no idea how far apart they are or how closer they are. No idea. You understand? So if I want epsilon, then I can make this something like epsilon by 2, epsilon by 2. If somehow this I can get rid of this term, okay, I'll be happy. You understand what I'm saying? So the trick is, the moment you tell me x and y are at a distance less than delta, and if x belong to, therefore the trick is, okay, if x belong to be xi ri and distance between x and y is less than delta, somehow I should conclude y also belong to be xi ri. Can I conclude? If I conclude, I will be happy. You follow that? Think about. Pause. You then proceed. So the trick is, okay, if I cut down this distance by half, therefore my delta is less than, let us say, ri by 2, then y will also be here, because distance between x and y will be less than or equal to distance between x and xi and distance between xi and y. Okay, then I can show that. Okay, just if you have problem, let's see. The point is, if x belong to vxi ri by 2 and my delta is less than, let's say, ri by 2, and distance between x and y is less than, okay, delta, right? Now I want to say y, this implies y also belong to vxi ri by 2. Why? This is what I want to claim. That's clear, because distance between, okay, y and xi does not include distance between y and x and distance between x and xi, right? Now this is less than delta and this is less than ri by 2, right? But this is also less than r by 2, therefore this. So what I have concluded? I have concluded, okay, not ri by 2, but I concluded ri. Okay, you follow that? Yeah, okay. Just again pause and proceed. Now the proof is extremely easy once you had understood what goes wrong with the intuitive idea. Okay, that is correct, but we have to improve upon that idea. So the actual proof starts with this. So let epsilon be given. Since x is continuous, since f is continuous, f is continuous at x. Okay, therefore there is an Rx positive, that f of e x Rx is contained in e of f of x epsilon by 2. Okay, not epsilon, epsilon by 2. Okay, you understand? That is distance between y and x are x dash. Distance between x dash and x less than rx would imply distance between fx dash and f is less than epsilon. Now let's look at the collection dx, not rx but rx by 2. Understand? That's the only change we are doing. This is an open cover. Since x is compact, okay, there exists x1 to xn, that the collection bxj r of xj by 2, okay, 1 less than or equal to j less than or equal to n is a finite sub. Is that okay? I will call rxj as rj. Okay. Right? Okay. Okay. Now what do? I will put delta to be minimum of r1 by 2 r, okay, right. Now let s and t be elements of x, that distance between s and t is less than delta. Then I want to prove, what do I want to prove? Distance between f of s and f of t is less than epsilon. Of course s and t are. Is that okay? Right. Now let us look at s. Now s belongs to x and x is union of t, xj and rj by 2, j equal to 1 to n. Yeah. Okay. Right. All right. Now you claim, we already proved it above, but let me claim t belong to xj r. Why? Because distance between t and xj I want to estimate. That is going to be distance between t and s and distance between s and xj. Is it okay? But this is by assumption less than delta, and this is by assumption less than rj by 2, but delta is minimum of r1 by 2 etc. Therefore it's also less than rj by 2. This fellow is less than or equal to rj by 2, but this is rj by 2. Rj, right? Therefore yes, t also belong to that. Now therefore distance between s and t is belong to that. Now what do I want to show? I want to show distance between fs and ft, right? So what will I do? So what do I have? I have the picture. This is my xj and my s and t. This is my rj. They are here within rj by 2. Yeah. Therefore this less than or equal to distance between fs fxj plus distance between fxj okay. Now what do I know? S belong to bxj and rj Therefore I know this distance is less than epsilon by 2, and similarly t belong to this rg, therefore in between this will also be less than epsilon by 2. So simply formally continue next. I hope all of you understand the proof. Okay, and for those who are not seen, I suggest look at the book by me, Topology of Metric Spaces. This is by Narza. And I suggest by second edition, that's only available. And this is what we did was theorem 4.29. Okay, so that's the end. Go through this, you can see the proof is actually very easy after a false start. I hope you like the proof. So thank you very much.